Thorough preparatory efforts are crucial to ensure easier and less stressful placement of concrete, ultimately leading to a quality result.
Our objectives for today are:
1. We need to be able to describe basic subgrade considerations and preparations. 2. We need to be able to describe how elevations are established. Lastly, we need to be able to identify and describe basic foundations. Being aware of your surroundings on a busy construction site is essential. It is crucial to use tools safely and wear appropriate personal protective equipment. Excavations pose significant safety hazards. Workers must follow occupational safety and health administration standards and implement protective measures accordingly. These protective measures can include sloping trench walls, shoring, or shielding, but the correct method depends on factors like soil classification, weather, surcharge loads, and depth of excavation. Workers should be alert for signs of soil shifts or water entry, indicating potential collapse, and a competent person should inspect the protective measures daily. Overall, safety must always be the top priority in concrete construction. Subgrade preparation is crucial for any construction involving slabs, foundations, or footings. A well-prepared subgrade ensures uniform support, while a poorly prepared one can lead to differential settlement and structural failures such as cracks. Some soils can expand when wet, causing further issues that need to be addressed to prevent structural failures. Subgrade conditions can vary due to soil type, density, and other physical properties. So it is essential to establish reference points and elevations through surveying and testing. On large construction sites, a survey crew handles this task, while on smaller sites, formwork carpenters may be responsible. The first step in subgrade preparation involves clearing vegetation, rocks, and topsoil from the construction area. Topsoil cannot be used as backfill. The site is then excavated to the established line and grade, ensuring uniform support for the concrete structure. Soft or problematic spots may need excavation, backfilling with good soil, and compaction to create a stable base. Problematic soils may require additional measures, such as reinforcing the soil with geotextiles or using a stable granular subbase made of materials like sand, gravel, or crushed rock. The objective throughout is to provide a base of uniform support, as uneven subgrade conditions can lead to cracking, differential settlement, and structural failures. Compacting soil reduces settlement, provides uniform support, and increases subgrade stability. And it is an essential step before constructing foundations, slabs, driveways, and sidewalks. The level of compaction is specified by the designer or engineer. Granular soils like sand require vibrating compaction equipment, while cohesive soils like clay need heavy tamping or rolling equipment. Optimum moisture content is crucial for effective compaction, with cohesive soils needing 5 to 8% moisture and granular soils requiring 10 to 15%. Compaction should not be done during rain or snow. In fill areas, uniform thickness and installation per project specifications are important for effective compaction. When constructing below the natural grade, the influence of groundwater must be considered. Its level can vary and change with seasons. Groundwater close to the surface can hinder subgrade and foundation preparation, necessitating dewatering to create dry conditions for construction. Dewatering methods include gravity drainage, pumping, or lowering the water table using well points and pumps. After construction, it's essential to keep groundwater away from foundation walls to avoid hydrostatic pressure. A drain pipe is often installed outside the foundation wall with a vapor-resistant membrane and perforated drainage pipe at its base to direct water away. The drainage pipe should be sloped to drain water properly, and a geotextile sock prevents debris from entering. Flowable fill is a thick, semi-liquid material used as backfill in utility cuts and trenches. It is a mixture of fly ash, water, and cement. Flowable fill quickly fills available space without the need for compaction, which saves both time and labor. The low compressive strength allows for easy excavation later with standard tools. Although more expensive than traditional fill soil, it is still cost-effective due to the labor-saving benefits. Flowable fill is self-leveling and can be colored as an indicator of utilities beneath it. There are several ways to establish dimensions and elevations. You can use an engineer's level, a laser level, or a hand level and string. Another option is the builder's auto level. Sight through the scope to the benchmark to determine its elevation. Then rotate the scope and sight on the leveling rod held vertically at the unknown point. The difference between the two readings will establish the elevation of the second point above or below the benchmark. This slide shows the basic concept of setting a level and establishing elevations from point to point. Point B is the known elevation. In this example, the point on the left must be raised 4 feet to be level with point B. With a laser level, only one person is needed to perform the work. To use a laser level, set the base of the rod on the benchmark. Turn the receiver until it faces the transmitter. Then slide the receiver up and down till it intercepts the laser beam. The receiver box will give a steady tone and show a bar when it is on target. Batter boards are temporary wooden stakes and horizontal boards built 3 feet to 4 feet outside the edges of a floor slab to mark corners. In order to indicate the foundation line, nylon string is stretched between the batter boards of each corner. Forms are placed using the string lines as a guide. If the slab dimensions are greater than the length of the screed available, then intermediate elevation points must be established inside the slab. To do this, use a level to transfer elevations from the forms to the top of a stake in the subgrade. Positive drainage should always be present on exterior concrete work. Sidewalks should always have slopes that drain the water off to the side of the sidewalk. The foundation must provide a solid and stable platform for the rest of the structure and transfer the weight of all materials above it to the ground. The type of foundation specified depends on the structure and the loads it will impose on the soil. Deep foundations consist of piles or caissons and are used for heavy loads such as tall buildings, buildings with basements, or buildings that are constructed on poor soils. Shallow bearing foundations are used for footings under walls and columns constructed on stable soils. Some basic types of footings are shown on this slide. They consist of a rectangular, square, or round slab of constant thickness. Reinforcing bars are placed near the bottom of the footing and run in both directions. Concrete foundation work is different from placing and finishing slabs. Since footings are normally below grade, their appearance is not important. There are 4 primary considerations in the construction of foundation footings. The soil load-bearing capacity should be tested and determined before placing concrete. Reinforcement must be placed per drawings and specifications. The concrete used must meet the specified strength, and the footing should be accurately sized and positioned to provide the intended support. Concrete can be cast directly against the earth as long as no standing water is present during placement.
Our objectives for today are:
1. We need to be able to identify basic form types and various types of concrete joints. 2. We need to be able to describe basic approaches to concrete reinforcement. Lastly, we need to be able to describe final inspections and the concrete ordering process. A form is a temporary structure that supports the placed concrete and determines its shape while it sets, hardens, and becomes self-supporting. The term formwork refers to the form, all form liners, and all the supporting members with their hardware and bracing. Forms and forming systems are divided into 3 broad categories as follows. Job-built forms are typically for one-time use and assembled from lumber on site. Prefabricated job-built forms are assembled on site from prefabricated components. Manufactured forms are purchased or leased from a form manufacturer or supplier. Effective forms can be made from many types of materials. Earth, plywood, dimensional lumber, and steel are the most widely used formwork materials. Fiberglass, precast concrete, aluminum, hardboard, rubber, polyvinyl chloride, and polystyrene are also used. A job-built form is depicted on this slide. Job-built single-use forms are built in place and may be fully demolished after use. However, the lumber and other materials are often stripped of hardware and cleaned for reuse. Built-in-place forms are used for both large and small jobs. Job-built forms are made of wood because it can be quickly and easily cut to shape in the field. Job-built forms for slab or foundation footings are braced by stakes at the corners. Use of prefabricated panel forms can reduce costs, increase precision, and save field labor. One type of prefabricated form, also referred to as a gang form, is shown on this slide. Prefabricated panels are often used for walls and concrete decks. These forms are available in standard sizes, usually in 2-foot or 4-foot widths. Prefabricated panels can also be custom-made to fit a specified need. You can also assemble standard-size rectangular panels to make one large form. Large gang form sections are lifted into place by a crane. The main types of manufactured forms include the following: pan forms, void forms, panel forms, column forms, and stay-in-place forms. Manufactured form systems are available for lease or purchase. Each proprietary panel system requires unique accessories for successful assembly. For some complex systems, workers must be trained and certified in the specific manufacturer's product line in order to be able to assemble their forms. Pan forms are commonly used in the upper floors of multi-floor buildings. They may be constructed of plastic, metal, or fiberglass. Pans reduce weight by displacing the volume of the concrete in the slab. Whenever the term void form is used, it is an indication that some material other than concrete is being used to fill space that concrete would otherwise occupy. Void forms may be used between a slab and expansive soils so that any upheaval of the soil beneath will not affect the slab. Panel forms are manufactured from either wood or metal and are assembled on site. As shown on this slide, they are typically used to form very large walls. As depicted in the figure on this slide, rectangular column forms are often assembled using smaller panels that may also be used for walls. However, there are also dedicated column forms equipped with hinge points at 3 corners and locking clamps at the 4th corner. Steel column forms can provide various shapes including round, square, and oblong. Stay-in-place forms remain permanently in place after concrete placement. They are made from steel and polystyrene because they do not significantly decompose. Polystyrene forms remain to provide insulation. Forms for slab-on-ground construction are not as complicated as those required for vertical structures. Many slab forms simply follow the perimeter of the slab. Large jobs use a combination of wood and prefabricated metal forms since they can be reused many times. There are many different styles of prefabricated forms for slabs, although any form used must be stiff enough to take the movement of vibrating and screeding the concrete as it is placed. The major types of hardware necessary to securely hold form systems together include the following: ties cross the form and keep it from spreading under the pressure of the concrete mix. Once the concrete is hardened, some ties are withdrawn while others are snapped off, leaving a portion of the tie in the structure. Anchors fasten the form to previously placed concrete. Hangers attach forms to a structural frame of steel or precast concrete. Spacers and chains hold reinforcing bars a specified distance from the inside surface of the form. Form liners are placed inside a form to produce a decorative finish on the concrete surface. The type and number of accessories and embedments required may influence the type of form and the hardware used for a specific job. It is important to make sure that any hardware does not interfere with the placement, consolidation, and finishing of the pour. Most forms must be treated with a form oil to prevent the concrete from sticking to the form. The best agents protect the form and help prevent it from absorbing water from the concrete. Barrier agents are simple materials and can include ingredients similar to motor oil or diesel fuel. For environmental reasons, many barrier agents are water-based and contain no petroleum products at all. Chemically reactive agents react with lime in the concrete and prevent sticking. As an added benefit, these agents tend to prevent wooden forms from absorbing water. Although more expensive than barrier agents, a lighter coat can be effectively applied, lowering its cost in comparison. The form surfaces must be clean and smooth before applying the release agent. The material is applied evenly by brushing, rolling, or spraying on the agent. Alignment of concrete surfaces is dependent upon all forms being properly aligned and square. Vertical wall forms should be checked to make sure they are level and plumb. Squareness can be determined by measuring the diagonal distance between opposing corners. If those measurements are not the same, then the forms need to be adjusted until they are equal, proving the form is square. Setting horizontal forms to proper line and grade is normally accomplished by using a string line or laser level. Once the stakes are set, the form lumber is attached. The forms should be staked and braced to keep them in vertical and horizontal alignment. The formwork is then situated and checked against those references to ensure accuracy. Before concrete placement begins, the formwork must have a final inspection. Formwork inspection will include a check of alignment, adequacy of bracing and ties, stability of the grade on which the forms are set and braced, and the application of a release agent. All reinforcement must be properly tied within the form. Remember, forgetting a single form tie can lead to a form failing. Concrete typically cracks as the result of tensile stress. Primary sources of stress include applied loads, curing, and the resulting shrinkage and temperature changes. Joints intentionally weaken the slab so that the inevitable cracks occur at the joints rather than at random locations. This type of joint is called a control joint. Jointing is also used to isolate a concrete placement from another structural member, such as a wall or column, so either can slightly shift without adversely affecting the other parts of the structure. This type of joint is called an isolation joint. In the image on the right, the area around the column has been blocked out with wood. The wood will be removed and joint material will be installed in its place before concrete is placed adjacent to the column itself. Control joints control cracking by weakening the slab and allowing the shrinkage stress to act on that point. You can make control joints with a hand groover while the concrete is still fresh, and you can identify joint locations in the project drawings. The thickness of a slab determines the depth and maximum distance between joints. As shown in the figure on this slide, minimum joint depth equals 1/4 of the slab thickness. Joint spacing in feet is usually 2 to 3 times the slab thickness in inches. The concrete sections formed by control joints should be as nearly square as possible. Control joints are applied to slabs on ground and some walls, but not to suspended slabs. Isolation joints allow a slab to move vertically or horizontally by isolating it from nearby parts of a structure. The rule for placing isolation joints is to separate the concrete from anything else that should not move. Isolation joint material is 1/4 inch to 1/2 inch thick. It is important that the joint extends to the full thickness of the slab to separate it completely from the structure. Construction joints and slabs on ground mark the end of a given placement. They should be spaced 5 feet or more from any parallel joint. They bond new concrete to existing concrete. They help transfer loads and stresses between the placements. Detailed drawings on the construction plans will show you how construction joints are to be fabricated. The figure on this slide shows 2 different methods of using dowels between placements to allow for lateral movement while limiting vertical movement. Water stops are applied across a joint to limit or stop the flow of water. Water stops may be used horizontally, such as along the base of a wall where it contacts its foundation. They are also used vertically adjacent to walls and control joints. They may be constructed of rubber, metal, or plastic. Hydrophilic materials absorb water and swell. The image on the right shows one application for water stop on a slab. One of the significant functions of reinforcement in concrete construction is to resist the tensile stresses caused by bending, shrinking, or temperature variations. Reinforcement in concrete is used to reduce the volume of concrete members needed to resist tensile stresses, resist internal pressure in concrete vessels, tanks, and pipes, resist the opening of cracks. The most common reinforcement material is steel. Steel and concrete tend to expand and contract together with temperature changes. The alkaline nature of concrete may help keep steel reinforcement components from rusting. Its isolation inside the concrete helps keep water and free oxygen away. Reinforcing steel for concrete is available as plain steel bars, deformed steel bars, welded wire reinforcement, deformed welded wire reinforcement, pre-stressing tendons, and post-tensioning cable. The most used steel reinforcement types are deformed bars and post-tensioning cables. Deformed bars are round steel bars with deformations that are rolled onto the surface of the reinforcing bar. The purpose of the deformations is to create additional surface area for bonding of the concrete and steel. The figure on this slide shows 3 standard types of deformed reinforcing bars. Each one has a different deformation pattern on the outer surface. Rebar comes in different sizes and various grades of steel. This information is stamped on each bar using a series of codes like the one shown on this slide. The primary code a worker should be familiar with is the bar size, which refers to the diameter of the bar. The image on this slide shows welded wire reinforcement placed in a slab on ground. It is used primarily in slabs on and above grade. The material consists of a square or rectangular wire mesh pattern. It comes in sheets or rolls with a variety of wire spacings available. The reinforcement in concrete must be properly tied, aligned, and located prior to the concrete being placed. The figure on this slide shows 5 widely used patterns for tying rebar. Never attach tie wires to the form or allow them to protrude from the concrete surface. Bar supports are necessary to keep vertical and horizontal reinforcement placed in the form at the required depth and far enough from the surface. The figure on this slide shows an example. In wall construction, side form spacers maintain the desired distance between the vertical face of the form and the reinforcement. All reinforcement should be inspected after positioning and again before the concrete is placed. It is important to make sure the job site is ready before the concrete is on site. Enough time must be allowed for a thorough inspection of the formwork, reinforcement, subgrade, and placement equipment without the pressure of fresh concrete nearby. The general rule for a final inspection is that everything inspected previously needs to be inspected again. Everything is usually inspected 3 times, with the last time being just before the ready mix truck leaves the plant. The subgrade should be checked for the following: uniform compaction, accurate grading, proper use of vapor retarders, and proper location of all drainage items. Formwork inspection includes a check for the following: alignment and elevation referenced back to the survey benchmark. All dust, mortar, and other debris removed. Bracing and ties are adequate. All form joints and seams tight and sound. The grade in which the forms are set and braced remains stable, and form release treatment has been applied. A check of all reinforcement includes the following details: reinforcement is properly set and tied. Reinforcement is supported as required to maintain proper depth and cover. Materials are freed from rust and scale. The amount of concrete needed for a placement is equal to the volume of the forms. The volume of concrete needed for a floor that's 20 feet wide by 50 feet long and 6 inches deep is calculated as shown on this slide. In this scenario, the contractor would likely order 20 cubic yards. This estimate provides extra concrete to account for waste or spillage. Before the first truck shows up, check the access roadway in and out. Access is an important factor as it affects the speed of placement and the quality of the final product. Consider the type and size of truck that will be arriving. Ready-mix concrete trucks are heavy and need a firm, dry site to park. Because of their weight, ready-mix trucks cannot go over curbs and sidewalks without causing damage. Therefore, plan the access paths to the point of placement with care. The most convenient way to obtain concrete is to get it from a local ready-mix supplier. The ingredients will be accurately batched, mixed, and delivered to the job site. You can specify the performance needed or the ingredients desired by recipe or prescription. When a strength level is specified, the ready-mix supplier is responsible to provide the properly proportioned mix. The delivery schedule must be carefully planned. The ready-mix supplier needs to schedule the batch plant and ready-mix trucks. And inspectors and other quality control personnel also need to be on site. The contractor needs to make everything ready to receive the concrete and have the placing and finishing crews on site with their equipment ready to work when trucks arrive. Everyone involved needs to coordinate with the delivery schedule. Every operation needs a hazard analysis during a team huddle before we start. Thanks for watching, and remember, you are the key to our company's success and safety. See you out there on site.